Hi all, welcome to this revision lecture on periodicity. I know this isn't the order that we learned these in last year, but I figured I'd just work through numerically. So let's make a start with 3.1, which is our intro to the periodic table. I would recommend while you're watching this video that you have a periodic table in front of you to reference. So if you need to do that, press pause, quickly go and grab that for yourself. All right. So we're going to be looking at all of these points. I'm not going to look so much at electron config because that is something that we've talked about in the electron config video. Please check that out if you're still not sure on electron configs. Let's start with just some general navigation by looking at the blocks. So we have the S, the P, the D, and the F blocks. So S block is, let me switch to highlighter, is helium plus these two columns here. You've then got the P block, the D block, which is our transition metals, and our F block, which I'll do in blue, which is the lanthanoids and actinoids. So those are named for the different subshells that are being filled up. So as we move across that D block, we are filling up the D subshell. Okay. Metals, non-metals, metalloids. If you're getting stuck, start with, yellow is a bad colour to try and write in. Start with boron up here and astatine down here and draw a diagonal line in between them. That line is the line of the metalloids. So everything on the right-hand side of these guys is a non-metal. And yes, helium is included in that. So non-metals. Metals is everything to the right. And that includes the lanthanoids and actinoids. Now, I've shown hydrogen here as a metal. Hydrogen's a bit weird. In some ways, it reacts like a non-metal in that it can accept electrons. In other ways, it acts more like a metal in that it can give electrons. So generally speaking, if you're asked about whether something is a metal or a non-metal, they will be more obvious. But the overwhelming majority of elements on the periodic table are metals. So groups and periods. So our groups are these vertical collections of elements. So groups have different chemical properties. That's how Mendeleev arranged the periodic table. So all of our alkali metals, which is group 1, they all react in very similar ways. They all react to different degrees with water. And as you move down the group, they become more and more reactive, but we will talk about that in a minute. So we've got our alkali metals, which is group 1. We've then got our noble gases, which is group 18. These groups are numbered on the periodic table that the IB gives you. Then just next to our noble gases, we've got our halogens, which is group 17. Then in the middle, this D block is our transition metals. Then we have our lanthanoids and our actinoids. If you get stuck on which one is which, have a look over here. So you've got lanthanum and actinum here. These two groups insert into this space here. So lanthanum is 57 and then it jumps to 72 for hafnium. Same between actinum at 89 and is that Rutherfordium? I think at 104. So those are the lanthanoids and actinoids. So working at electron config, basically let's do aluminium. So this is 1s1, 1s2, 2s1, 2s2, 2p1 to 2p6. Then you've got 3s1, 3s2, 3p1. So what your electron config ends up looking like is 1s2, 2s2, 2p6, 3s2, 3p1. So you can work out electron config by basically counting across the periodic table. Remember that there is some electron config weirdness that happens in here with chromium and copper. But again, that is covered in the electron config video, so I'm not going to go into masses of detail on that. Okay, so let's move on to periodic trends, which is 3.2. So we are going to go through the trends in the periodic table, metallic and non-metallic, and the oxides. We're going to basically trends in metallic and non-metallic character. It's based on their position. Sorry. So we're going to talk about chemical properties trends and acid-base character. Yes. So atomic and ionic radius. So basically what we're talking about, sorry, I keep trying to pick what pen color I want to use. Atomic radius is, for a given element, what is the distance between it and its outer shell versus what is the distance between this thing and its outer shell if it's gained or lost electrons. So think about what happens when I move along. Basically, think about what happens when I move along a period in the periodic table. My shell, that outer shell I'm filling, is the same shell. So I'm filling the same shell, but I'm increasing my number of protons, which increases the pull on the valence electrons. So because I've got that increased pull on the valence electrons, something like fluorine is going to be smaller than beryllium, for example, because I'm adding electrons into the same shell, so those electrons are the same distance away, but that pull of the fluorine nucleus is stronger because there's more positive charges in there. So as you move along a period, that outer shell is being pulled in closer. As we move down a group, though, I am adding shells. Therefore, my radius is much larger as I move down a group. Okay. So ionisation energy. Quick definition. The ionisation energy is the energy required for me to remove an electron from something. So let's think about periods exactly the same way as we just did. As I'm moving along a period, I am not changing the distance between my nucleus and that outer shell, and I'm increasing the positive charge in that nucleus. I'm increasing the number of protons, which means that as I move along a period, I am increasing the effective nuclear charge. Which makes it harder to remove electrons. Now, in the HL periodicity video that I made, we do discuss some of the discontinuity. So if you look at a graph of first ionization energies along a period, it isn't quite increase. It's slightly more complex than that. If you're interested, do check out that HL video. As we move down a group, again, I'm adding extra electron shells. So it's much easier for me to remove an electron from, so fluorine. Okay, so we've got fluorine, then chlorine, then bromine, iodine, and astatine. So it's much easier for me to remove an electron from iodine than it is from chlorine. And that's because, thinking back to our previous slides, the outer shell of an iodine atom is far further away from that nucleus than the chlorine is. So it's easier to remove that electron because that positive charge of the nucleus is more distant. All right. So electron affinity. Again, let's start by looking across this row, but let's put elements to it. So, pen. So we've got lithium here and fluorine over here. Now, in terms of your general knowledge about how these things react, fluorine reacts by gaining an electron. It wants to gain that electron. So the electron affinity, how much fluorine wants an electron, that's a lot higher than it is for lithium. And that's the trend we see. As we move right, electron affinity increases. So its want for electrons increases. It works the opposite way to ionization energy. If something wants electrons, it's not likely to want to get rid of electrons. And hopefully you're starting to see some patterns about how the logic goes as we move down groups. The further away that outer shell is, the less pulling power of that nucleus, which makes it harder for that nucleus to actually attract an electron into that outer shell. Think about how hard it is to pick something up when it's close into your body compared to when it's up the top of a very high shelf. If you're just grabbing onto it with your fingertips, it's a lot harder to grab onto it than it is if it's close to your body. The same thing goes with electron affinity. As we move down a group, because that outer shell is further away, it's harder for the electron to be grabbed by the attractive power of that nucleus. Okay, so electronegativity is, so if I have X covalently bonded to Y, those electrons are not necessarily shared equally. The only time they are is if X and Y are the same type of atom. A lot of the time what will happen, my electrons will actually spend more time around one of my atoms than the other. Imagine it like a year 7 kid having a tug of war with a year 12. The year 12 is likely to be larger and stronger, so it's an uneven tug of war. So as we move along a period, electronegativity increases. Change to pen, electronegativity increases. So fluorine is much more electronegative than lithium. We also have to think about changes in electronegativity. Let me just change my highlighter colour. As we look along groups. So as we move down a group, that outer shell is getting further away, which means that as I move down a group, electronegativity decreases. So the most electronegative element is fluorine, followed by oxygen. Sorry, quite confusing that I did that in green as well. So fluorine is the most electronegative, followed by oxygen, chlorine, and nitrogen. So basically this top right corner is the most electronegative, and something like francium would be the least electronegative, because these electrons, we've got a high core charge, so a large positive charge in the center, but also those electrons that are being bonded and shared are quite close. So later on, when we talk about bonding, we'll talk about hydrogen bonding, which is FON. So metallic versus non-metallic character. As I move along my period, my elements go from, and this is actually a pretty decent example. So we've got metals, metalloids, and non-metals. So as we move from left to right across a period, remember metal, non-metal, metalloid, those are defined by characteristics, the way these things react. And for all of the reasons that we've been discussing throughout the last nearly 20 minutes, we know that these guys are the most non-metallic. Same thing goes in the other direction. So if you pick like one of the columns, like with oxygen up the top, or even nitrogen. Nitrogen's probably a better example. So you've got, and that's even the one I indicated. So you've got nitrogen, which is a non-metal, phosphorus, which is a non-metal, arsenic, which is a metalloid, antimony, which is metalloid but mostly metal, then bismuth, which is definitely a metal, and then according to the periodic table I've got, that one doesn't have a name yet because we haven't been able to confirm that it exists for long enough to give it a proper name. So as we move down group 15 there, you can see that we're going from a non-metal in nitrogen through to something quite metallic in bismuth. So as you move down a group, those outer electrons are getting further away, which means that we're seeing an increase in metallic character. Okay, so within the group, we've got different trends. So let's start with our halogens, which is group 17. So that's fluorine, chlorine, bromine, iodine, and astatine. Now these guys react by gaining electrons to form negatively charged ions. So in the context of all of the stuff we've just been discussing, electron affinity decreases as you move down this group. So fluorine is going to be much more reactive than something like iodine, because those outer shell electrons are closer in, which means that it's better able to attract an electron into that outer shell. The opposite logic, well, actually the same logic but in the opposite direction, works exactly the same for our alkali metals. So we've got lithium, sodium, potassium, rubidium, cesium, and francium. I'm not sure if it's francium or francium. I say francium. I don't know why. So these guys react by donating an electron. These are metals. Now, in lithium, that outer shell electron is much closer in, so that nucleus has a tighter hold on that electron in lithium, so it doesn't react as readily. But in francium, that electron is miles away from the nucleus, so it jumps off, basically, if you look at it the wrong way. In the description, I will put a link to a periodic table of video reacting these different alkali metals with water. These things react quite explosively with water. I believe last year I reacted sodium and potassium with water, but in the periodic table of videos link that I'll give you, they actually take it the next step and react rubidium and cesium, which is kind of spectacular. These trends, take-home message, these trends that we are looking at come back to exactly the same stuff we've been talking about for the last little while. It's all about how far away are the electrons and how much effective positive charge do we have in that nucleus. These are all in the same group, so we only care about distance. The effective core charge isn't changing as I move from lithium to sodium or fluorine to chlorine. What's changing is the distance of that outer shell from the nucleus. Okay, so you need to know about the period 3 oxides. So basically how it works, we start off by one, ignoring argon, because argon doesn't really react with oxygen. We start off with sodium and magnesium, which are basic. We've then got aluminium, which is amphoteric. Then you've got your silicon oxide is a covalently bonded. So then think about the acid deposition unit that we did. We talked about sulfur oxides as being one of the main sources of acid rain. So phosphorus, sulfur, and chlorine are all acidic oxides. So sodium oxide, Na2O, or magnesium oxide, these both react with water to make effectively aqueous hydroxide ions. Aluminium, so aluminium oxide can react with HCl when it's acting as a base, or it can react with sodium hydroxide and act as an acid. So that's what we mean by amphoteric. It means it can react with either an acid or a base. Now, phosphorus, sulfur, and chlorine react. So phos P4O10 reacts with water to form phosphoric acid. Sulfur oxides, again, as we looked at in the acids and bases acid deposition, that forms H2SO4, which is sulfuric acid. It can also form SO2 plus H2O to form sulfurous acid. Again, I will go through that again in the acids and bases. Then we have Cl2O7, so that, and I'm not going to balance this, it forms 2HClO4. Actually, that might be balanced. That is balanced. Wow. So that is there's a particular name for that acid that is completely escaping me, but you need to know how to construct these equations. So P4O10 and Cl2O7, you might need to actually remember those formulae. But things like the oxides, so sodium and magnesium and aluminium oxides, those ones you should be able to work out from positions on the periodic table, but I'll talk about that when we get into the bonding topic. These guys here you might have to know. But SO3 you already know from the acids and bases. Already will know, given that it's a later topic. I don't know. I'm not an English teacher. Okay. So these are the points that we've talked about. We talked about the blocks of the periodic table. We talked about groups and periods. We talked about period number. Did we talk about period number? That's just the number of the row on the periodic table. Valence electrons, periodic table shows positions. Yes, 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 yes. Okay, so we talked about trends in vertical and horizontal. We talked about metallic and non-metallic, and we talked about oxides. I explained how we can predict whether something's a metal or a non-metal based on its position on the periodic table. We talked about comparing two different group 1 elements with each other and two different group 17 elements with each other. We talked about these. We didn't talk about nitrogen, but again, nitrogen comes up in the acid deposition topic later on, so I might hold off on that. General trends and group trends. Fantastic. Thank you so much for sticking with me through this. Thank you so much for your attention. If you have any questions, if you could fire us an email and let us know, and I will get in touch with you. Otherwise, have a fantastic rest of your day, and I will see you next time. Bye.